All right. Hello, everyone. Welcome back. So, in this video, we would like to talk about various optoelectronic materials. So, we have understood how the optical emission process happens. Uh, so, we would like to understand the materials in a slightly deeper fashion. So, to do that, I want to start with this graph here. This shows the evolution of light sources over the last 50 to 60 years. Right. So here you're seeing time in the x-axis and luminescence efficiency in the y-axis. So essentially, if you have a higher lumen per watt, that means you have more efficient light source, then it's brighter source. Okay. And if this is a logarithmic scale, you're going from zero point 0.1 to 100 lumen per watt. So what you see is the traditional, the old incandescent bulbs, the Edison's bulb, and then the incandescent lamp that it was used in 80s and 90s also actually. They're not very bright sources. Okay, but nowadays with in 2000s and 2010s, last decade, you see that more and more CFLs and then LED lights are coming, which are actually very bright. So on the logarithmic scale, there is a significant improvement in the luminescence efficiency. Also, if you look at the x-axis, in the 1970s, we had red LEDs, that were possible. The technology was just getting developed at that time. And over time, we started having various different materials. And you see that the efficiency is improving, and also we are moving towards, green and orange and so on. So various combinations of lights were possible. Okay, so if you look at the visible light, you have the wavelength range of 300 nanometers to 700 nanometers. Let's say you want to simulate, you want a light that simulates sunlight. You want to have a white light. So then you should have, if you look at the spectrum of that, you should have all the wavelengths possible. If I have, let's say this is lambda, this is intensity, ideal white light should be flat. You have same intensity at all wavelengths, but that's never going to be possible. Even sun has a certain peak, and then there is some variation in the spectral intensity, spectral energy density, right? So what we would like to do is, have a source which emits at different wavelengths. Okay, but we've already seen that for a particular material, the band gap defines where the emission happens. So is it possible to have a wide range of band gaps in the same material? Well, of course not, right? We are not going to have that. Okay, so we'll have to tune the band gap, and that is essentially what is shown here. You see that in the in the beginning in about 80s, you started introducing arsenic. This is a compound semiconductor. We have so far seen elemental semiconductors, which are silicon, germanium. We have seen gallium arsenide, which is a compound semiconductor. We call it a binary semiconductor, binary compound semiconductor, because it has only two elements. You could also have gallium arsenic phosphorus, which is a tertiary compound semiconductor, which has three elements. Or you could have quaternary compound semiconductor, such as aluminum, indium, gallium phosphide, and so on. Okay, it will become clear why we want these structures. Okay, in a short while. And the other important trend you see is that starting about 90s, there's a very significant development of nitride semiconductors. Okay, starting with gallium nitride, which actually has a band gap of 3.3 eV. So it can actually be tuned to give you emission in the blue spectrum. Okay, and sometimes even in the green spectrum. So you can have these nitrides which are giving you very strong emissions, and they are significantly developing. So a Nobel Prize was given for the invention of blue LED in the last, I think in 2014, I believe. Okay, so there's a lot of improvement. So the trend over the last 50 years has been increasing in the luminous efficiency, and also various material combinations that are possible. So we left the initial gallium arsenide based devices, and a lot of different combinations are being used. Okay, so you already understand why we need to go for compound semiconductors, because silicon and germanium are indirect band gap semiconductors. They are not useful for light emission. Okay, because of that. So you need to have direct band gap semiconductors, and the combinations. This slide shows you various combinations that are used. Okay, but to go back to the basic question, what sort of band gap is good, right? What sort of band gap needs to be realized for a particular wavelength of emission? So we know the relation between wavelength and band gap, right? So this is lambda equal to 1.24 divided by Eg. So this Eg is in EV and lambda will be in micrometers, right? If you put lambda in micrometers and Eg, you will get, I mean, for example, a certain band gap, let's say 1 EV, will give you a lambda of 1.24 micrometers, okay, and so on. So, how do we change this? How do we change the band gap? Well, so far we have only seen three materials: germanium, silicon, and gallium arsenide, which have their characteristic band gap. Is it possible to get something in between? And if so, how do we get that? And the way to do that is, the approach is actually described in this slide. So here on the left, you see on the x-axis, we see mole fraction. I'll describe in a moment what mole fraction is. On the y-axis, you have energy gap. Okay, so we have two well-known materials, which is the first one is gallium arsenide. Gallium arsenide has a band gap of 1.42 eV. So I'll put gallium arsenide at 1.42 eV. So here, somewhere here, Eg of 1.42. Okay, and you have gallium phosphide, which is an indirect band gap semiconductor and which has a band gap of about 2.26 eV. Okay, so I'll take gallium arsenide, gallium phosphide. I'll put its band gap at 2.26 eV. Okay, these are the naturally occurring materials, and we can synthesize them and actually have a highly pure substrate with this. Okay, so now what if I want to have a band gap in between them, in between 1.42 and 2.26? Is there a way to get it? It turns out that there is a way, and the approach is actually to mix the semiconductors. How do we mix the semiconductors? Well, what I can do is I can replace an arsenic atom with a phosphorus atom. If I do that, I'll increase the band gap slightly. But of course, it never happens that you replace one atom, you replace in a significant quantity. For example, if you take silicon, what is the atomic density of silicon? We saw that it was 5 into 10 power 22. Well, for gallium arsenide, it might be something slightly higher than that, but in the same order of 10 power 22. Okay, so now you replace about 0.5 into 10 power 22 atoms, and you remove 0.5 into 10 power 22 arsenic atoms and replace them with phosphorus. What do you expect, right? So that process is known as mixing semiconductors. And now the way we do that is, let's say I have gallium, and here you're having arsenic. Okay, I'll take let me replace. For example, you have gallium and arsenic, right? Let's say there are n atoms of gallium and n atoms of arsenic in your material. Okay, you can think of this in terms of per unit volume. Okay, now I'll replace, let's say there are two arsenic atoms in the unit cell. Okay, I'll replace one arsenic atom with a phosphorus. Okay, so what I'll do is, instead of n, let me use 2. Okay, let's say there are two atoms of gallium and two atoms of arsenic in a unit cell. Just as an example, okay, it's just for discussion purposes. Okay, so now what I'll do is I'll replace one arsenic atom with a phosphorus atom. So instead of this, gallium will remain 2, but arsenic I'll have one atom and phosphorus one atom. What did I do? Well, now I created a structure which has gallium and then arsenic 1 minus x, phosphorus x. Okay, where my x is a mole fraction, I call it. If you sum up both 1 minus x and x, you get 1, right? So this combination is going to be remain 1, and this will be 1 anyway. So the overall count of atoms is going to remain the same, but some of the atoms you remove. Okay, if of course, in a lattice you have, in a material you have huge number of unit cells, and in some of the unit cells you replace, some of them you don't replace. So essentially, you can have a mole fraction which is changing from x equal to 0 to x equal to 1. Okay, so what I can do is, if I make x equal to 0, what am I doing? Well, I'm essentially having all arsenic atoms only. So I have gallium arsenide. If x equal to 1, I'm essentially having all phosphorus atoms. So it becomes gallium phosphide. Now, what if I do some combination? What if I choose x equal to 0.5? If I do that, gallium, for every 2 gallium atoms, there is one arsenic atom and one phosphorus atom. That's what it means. When I say mole fraction of gallium arsenic phosphorus 0.5, zero point 0.5, that means for every two atoms of gallium, there is one arsenic atom and one phosphorus atom physically. Okay. So why is this useful? Well, it turns out that we have seen already that band gap of gallium arsenide is 1.42. On the other extreme, you have gallium phosphide, which has a band gap of 2.26. Now, a combination of this, as I change my mole fraction from 0 to 1, will have a band gap from 1.42 to 2.26. Okay, so this is a very important, very interesting idea to generate various band gaps, because naturally occurring, good quality substrates are very limited, right? So how do we overcome that? By this process. What is actually happening in the energy band diagram perspective? Well, this is an EK diagram. So we know that gallium arsenide is a direct band gap semiconductor. So the valence band maximum and the conduction band minimum will coincide. All right. So now, if you excite, you somehow introduce electrons in the upper level and the holes into the lower level, they'll recombine and give you a photon, which is shown here. Now, this is at x equal to 0. And if I increase the mole fraction, I increase x from 0 to, let's say, 0.2. Okay, what would happen? Or in this case, 0.4 is shown. So you have the valence band doesn't change so much, but the conduction band changes in this fashion. So there are two values. One is this main value at L equal this crystal momentum 0, and at some other point you have different k, you have a different value. Okay. So now as you increase to 0.4, this gap is increasing. That's why the band gap is increasing as x is increasing. Now, if you cross x equal to 0.5, for x equal to x greater than 0.45, sorry, if you increase, x beyond that, what is happening is this peak is going much, much higher. And then now the minimum of conduction band occurs at here, at this point. Okay, the minimum of conduction band, right, CB, occurs at k not equal to 0. K equal to 0 is what we want, right? Because that's the direct band gap. But now, if you go, for example, take this guy 0.85, the peak is here, but then the smaller peak and the lower peak is here. So the band gap is going to be this, right? This minus this. This is going to be band gap, and it's an indirect band gap, not a direct band gap. Of course, there's always this direct band gap line which is there, but finally the material, the band gap we define is the minimum of the conduction band and the maximum of the valence band. So after this point here, EG is indirect. Okay. Below that, it's a direct band gap semiconductor. So this is how you can tune tune materials to get various band gaps. It sounds quite simple. Well, conceptually it is simple, but practically it is quite complicated. And the way to understand that is by this. Let's say these are various substrates for optoelectronic devices. Okay. So the reason I'm discussing this is, whenever you have semiconductor devices, we want very, very pure materials and large sizes. For example, silicon, we can purify it to 9N levels, and then we can have wafers which are about 1 feet in diameter, 12 inches in diameter. Okay, and this is very, very well developed technology, relatively cheap nowadays. Okay, so silicon is easy, and even germanium is actually available quite easily. Okay, it may not be the same diameter, but you can get it quite cheaply. But gallium arsenide, if you want, gallium arsenide wafers are available, but they are more expensive compared to silicon. And also, the diameter of the gallium arsenide wafer is much smaller. We can only typically get up to 4 inches in diameter. Okay, that's about 12 centimeters. So, if you have, indium phosphide, which is another commonly available substrate, this is even smaller diameter, and it's much more expensive. But it turns out that indium phosphide is very, very useful for high performance electronics and optoelectronics. Okay, we cannot live without this. So this is still, used. These are some of the common substrates for semiconductors or optoelectronics. In addition, there are various substrates like silicon carbide, aluminum oxide, alumina basically. This is sapphire, which is used for gallium nitride devices, and gallium antimonide and so on. These are also available, but you don't get large size crystals. The crystals might be a few square centimeters. So the whole reason why semiconductors became cheap is that we are able to grow large crystals, and we can fabricate many devices at the same time, right? The whole integrated circuits we can do. But if you have small substrates and you fabricate one or two devices, it's not going to be economically viable. Okay, so it turns out that there are these few substrates, and if you want any other material, for example, gallium, arsenic zero point 0.5, and phosphorus zero point 0.5, you can't really make a substrate out of it. Okay, what we have to do is we have to grow it on an existing substrate. So these are the three main substrates that we have, and a few others. So how do we grow them? The process we grow is called as epitaxy. Epitaxy, it's derived from the Greek word, it's given here. Epi means upon, so on top of something. Taxis means order. So you maintain the same order, same crystalline orientation. That is what epitaxy means. So an example would be, take a substrate. I could take, for example, gallium arsenide. Okay, and then I grow a buffer layer. This is for growth reasons. For now you can just accept it. Right? It's some sort of combination. On top epitaxial layer, I want gallium, arsenic 0.5, phosphorus 0.5. If I want that, I need to have a small buffer layer, and then I can grow this material. What this sounds simple enough, but in practice you need to satisfy a condition which is known as lattice matching to actually grow efficiently. Okay, and that is what is shown here. So this is a slide image which is taken from Jaspreet Singh's book. I mean, if you want, you can go back and refer, but you don't need to do it for this course. So what I'm showing you is three different scenarios. So, well, you have an initial substrate. These dots are representing the atoms, and the lines are representing the bonds. So you have a substrate, and let's say your substrate is exactly having the same lattice constants as the material that you want to grow. Okay, so the same sizes, right? These two are there. One is dark and one is gray, that's all. And if you grow them, then you have what is known as perfectly lattice matched material. Okay, what we mean by that is there is a same one-to-one correspondence between the substrate and the epitaxial layer. And this is really very hard to get if you have dissimilar materials. If I try to grow gallium arsenide and gallium arsenide, then I can get it. If I try to grow silicon and silicon, maybe I'll get it. But if I want to grow germanium on silicon, well, it's not going to be perfectly lattice matched. There are going to be some constraints. What are the constraints? Well, let's say because if you're let's say you want to grow silicon and silicon germanium. We saw that silicon germanium was used in the 90 and 65 nanometer technology. Okay, in 2000 to 2003 time frame, 2005 time frame, right? They introduced silicon germanium. So what we said was that is strain. We said, how is the strain happening? Well, silicon germanium is going to have a slightly different lattice constant from silicon, right? So you see that larger unit cell here. Okay, this is just a qualitative depiction. It's by no means the actual physical thing. It's much more complicated. Okay, so this is a slightly larger unit cell, and then you try to grow on this. What happens? There is one possibility. That is, the lattice of the layer that you're growing tries to adjust itself to the lattice which is laying in the substrate. Remember, this is basically about 500 microns of wafer, 500 micrometer wafer. It's a big bulk wafer. On top of it, you're trying to grow a thin layer, maybe 2 nanometers or 10 nanometers. It just depends, what you want. Okay, and there's a whole procedure for this. It's called as molecular beam epitaxy. It's quite detailed, and we don't need to get into it. In a technology course, somebody might teach you that. If you're interested, you can learn by yourself. Well, what happens is, if you try to grow the silicon germanium on top of silicon, you will see that in the x direction, the lattice has shrunk, but in the y direction, it has become stretched. So this is called a strain. We stretch it or compress it. Okay, what happens if you do that? In the discussion, we said that it enhances the mobility, and it can be used. For example, in the NMOS devices, there was tensile strain applied, and then in the PMOS devices, is compressive strain. If you do that, the mobility was improved, and that's how they managed to improve the drive currents in the 65 and 90 nanometer technologies. Okay, something similar happens, and you get a different material. You're able to grow. Okay, if you want a perfectly pure silicon germanium, then you have to use the entire substrate differently. And if you try to grow very thick materials here, invariably what happens is this will have some, what we call as defects. What is that? Well, suppose if this strain is not happening, somehow the lattice configuration is such that, let's say you're trying to grow gallium arsenide on silicon, the lattice constants are completely different, then it will not work. Okay, what will happen? Well, what happens is you have the substrate, you have a epitaxial layer you're trying to grow, but instead of having one-to-one correspondence between the substrate and the epitaxial layer, it will try to grow in whatever default, its lowest energy state. So it will try to maintain the same lattice constants. If that happens, you will see that some of the atoms are not bonded. There's no one-to-one correspondence, and some of them are stretched here like this. So you can have a whole variety of defects that happen, and because of that, you see here that this is a picture again from the same book. So you want to have a perfect, neat, lattice. Instead of that, sometimes a particular lattice atom might be replaced by another atom, which is called a substitutional impurity. So because of that, the whole lattice around it is distorted. Similarly, you can have an impurity in between the lattice sites. So you saw that in a unit cell, the corners and those face centered and body centered and all that, you have these atoms. If somehow a lattice, atom goes and sits somewhere in between, we call it as an interstitial impurity. So that can happen, or it can be an alien atom, or it can be a same atom. I mean, it's just whole lot of combination. You can sometimes there might be a missing atom, so that's called as a vacancy. So a whole range of defects can occur, and we don't like them. The reason we don't like them is, let's say you have a certain band gap of let's say this is your EV and this is your EC. If let's say there is this trap, or this we call as traps or defects, right? Defects in the lattice. If you have these defects, they will end up as a level in between the energy band gap here. When you have energy levels in between the band gap, then that will cause recombination. So we are creating electrons and holes in the electron hole pairs, and these electron hole pairs can recombine through the trap levels, and because of that, you can actually lose the functionality that you're trying to achieve. You already saw that recombination is proportional to the difference in the energy, inversely proportional rather. If your energy difference is large, then the recombination probability is small. Okay, same as generation, just the inverse process. But now if you introduce a trap level, you are actually having small, higher probability of this transition happening, higher probability of this transition happening. So the overall probability will increase. Okay. So this is a second order process, but it is significant enough for us. And in optoelectronic devices, it's absolutely undesirable, because whenever electron recombines through this process, it does not emit radiation that we like. Right? It's emitting, maybe it is just emitting as heat, or it's emitting at a different wavelength, which we still don't like. Okay. So whenever you have defects in a lattice, they sometimes show up as, we call them color centers. They give a different color. For example, if you have a defect in a sodium chloride lattice, it will show up yellow. And there are many, many things like that. Anyway, I'm getting distracted. It's not necessary for us right now. What I wanted to convey is you have this lattice matching that is very, very important. And this is not easy to achieve. You can't arbitrarily grow any substrate. For example, if today I dream that I want arsenic 0.35, phosphorus 0.65. Maybe I'll grow it, maybe I will not be able to grow it. How do we decide that? Well, to decide that, we need to look at a diagram of lattice constant and energy band gap. Okay, this is a diagram that will help you to choose the composition of what we can achieve technologically. This is a very, very interesting diagram. I like it very much because it explains the concept of lattice matching very well. And you can spend a lot of time analyzing this, and you'll automatically understand what is suitable. So in this picture, you have the x-axis as the lattice constant, y-axis is the band gap. Okay, so now there are various materials on the x-axis here. Gallium arsenide has a lattice constant of 5.65. Indium phosphide has 5.85 angstroms, and so on. Many different materials. There are 6 to 7 materials here which have their lattice constants. And what are their band gaps? The band gaps are given in the dot here. So for example, gallium arsenide has a band gap of 1.42 eV. That, the corresponding wavelength is given on the right side. Just the same, the relation anyway to convert. So 1.42 eV will correspond to 870 nanometers, okay, 0.87 microns. That's what you're seeing. Similarly, if you take indium phosphide has a band gap of, I think, 1.34 eV, okay, and it has an emission around 920 nanometers. So you see that. So by looking at this, you can analyze, what are the band gaps and what are the wavelengths. Okay. Another interesting thing is, let's go back to the discussion we had about gallium arsenide and phosphorus, right? That's the discussion we had initially. Let's go back. So this was the combination, right? So we had gallium arsenide and gallium phosphide. Let's see what happens when you combine them. Okay. So on this picture, you have gallium arsenide here and gallium phosphide here. Okay. So when you combine them, you see that there is this line which is showing you that the band gap is increasing. Okay. And then aluminum arsenide, it's going to gallium phosphide, which is an indirect band gap. So this dashed line shows you indirect band gap, and a direct band gap is a solid line. Okay. So just as we have explained in the using the band diagrams, you have this line which is appearing. Now, can I grow that? For example, I want to grow this point, gallium, let's say arsenic X, phosphorus 1 minus X. Okay. We want to grow that. Can we do that? Well, it's going to be challenging. The reason is there is no substrate available on which we can grow this material. On the x-axis, you don't have a suitable substrate. So how do we achieve emission in the red region of the spectrum? Well, that is achieved if you look at this particular line. If you pay attention to this line, this is a combination of gallium arsenide and aluminum arsenide. Don't choose phosphorus, choose aluminum. Okay. So what you should do is, let's say this, just remove that. So instead of that, I'll say gallium arsenic 1 minus X, aluminum X. Okay, I choose this combination. So if I put X equal to 0, I get gallium arsenide. If I put X equal to 1, I get aluminum arsenide. If I choose somewhere in between, I get a different band gap. The interesting thing is gallium arsenide has 1.42, aluminum arsenide has 2.2, maybe 2.22 something, 2.5. In between that, you have this line. The beautiful thing is both of them have very, very close lattice constants. So because of that, there's a straight or nearly straight line here. And so it tells you that if I want to, let's say, grow this X equal to 0 to X equal to, let's say, maybe 0.5 or something here, you can grow it on top of a gallium arsenide substrate. So this has the same lattice constant as a gallium arsenide. So I can grow this structure. By doing that, basically I can take gallium arsenide wafer. On top of it, I'll choose this epitaxial layer of gallium, aluminum X, arsenic 1 minus X, whatever, you can do that. Okay. If you do that, it is going to satisfy the lattice matching condition because they're in the same direction. So whenever you have straight lines, you can grow those substrates. Okay. That is what we are looking for in this diagram. Let's take another example. Let's say, okay, if you grow this, essentially you get 700 nanometers light. Easily you can get 700 to 800 nanometers. You can tune it and you can grow various materials, and we can get lasers and LEDs. Another wavelength of interest would be 1.55 microns. I told you that for telecommunications we use 1.55 microns wavelength. And what is the energy corresponding to that? Well, the 1.55 micron is here, right? And this corresponds to 0.8, roughly 0.8 eV. This is a line. So I want to grow this. What do I do? Well, when I look at this immediately, it looks like, I want to be on this substrate. Can I use indium phosphide? No. Indium phosphide looks to be a great material because it has the same lattice constant as the line that I want, right? Vertical exactly on the same line. But it turns out that indium phosphide's band gap is actually much higher. It's 1.34 or so, right? So we can't use indium phosphide for, if I'm interested in any optoelectronic device at 1.55 micrometer, okay? This is critical. If you don't have it, there's no internet, right? Because if you don't have it, there is no fiber optics, right? You are sending this signal at 1.55 and you are laying fibers, connecting continents, and we are able to have instant communication. So this is so critical, and you can't use indium phosphide. So the challenge for you is to think about what sort of combination can give you wavelength of 1.55 micrometers. Okay. So the obvious, choice seems to be, the first choice seems to be, okay, let me use this, let me use this combination, right? I'll use a combination of gallium arsenide and indium arsenide. Okay. I'll start replacing some arsenic, some gallium atoms with indium. Can I get it? Well, you can change the band gap. It's beautiful. if you use this combination, this is basically gallium X, indium 1 minus X, arsenic, right? So you're having this sort of compound semiconductor, tertiary semiconductor, and it's always direct band gap. It's beautiful, but the problem is at at the substrate that you have, right? At this point, it is having, it's not having really the same lattice constant. So if you want to use this material, you could still try. I mean, you could try because, you will, if you grow it on indium phosphide, you have to be somewhere here, right? This one. So indium phosphide's lattice constant is probably 5.87 angstroms, and your gallium indium arsenide's lattice constant is going to be 5.2 angstroms. There is some amount of lattice matching. Okay, so if you actually study this in greater detail, if you look at the mismatch, you can try to predict how thick you can grow. Okay, that's for material science. I don't want to get into all that. So it is possible to grow it, and people have done it, but it's still not ideal because there is we want to minimize this difference in the lattice matching. Okay, so another option is to choose this particular point here on this line. But this is a very, very complicated thing because you have to use a whole combination of indium arsenide and antimonide and gallium arsenide and so on. So if you try to go on this line, you have to use maybe 4 compounds instead of 3 compounds, and with that you can get a much better lattice matching with indium phosphide. Okay, so this is challenging, but scientists have done it with quaternary compounds. They're able to get very good emission at 1.55 micrometers. Okay, so this is by no means simple. I mean, it is a very, very complicated process. And I mentioned the Nobel Prize in for blue LED, right? The scientist was actually, one of the scientists was Imano, and he was actually a PhD student, and he spent 5 years of his life or so trying to develop the process. And then later on, after 10, 20 years, he got a Nobel Prize for that. Okay, so it's a very, very challenging work, but scientists have figured it out. And if you're interested, of course, you can look at all the details later on. All right. So this is basically the quantitative picture. You could take another example. Let's say I want to design a laser which has a wavelength of, let's say, 900 nanometers. What do I do, right? You think about it. Okay, 920 nanometers or so. You think about what can be done. All right. Or rather, yeah, I leave it to your imagination. 820 nanometers maybe, something close to that. Okay, so yeah, think about it and analyze this. Stop the slide here and spend a lot of time. The reference, this is taken from this reference book, again, Schubert's book. So you can go and refer to this, and you'll find a lot of material on LEDs and lasers in this book. Okay. All right. So with that, I would like to stop the discussion in this video. So we looked at the various materials or material aspects of optoelectronic devices. So I'll stop. And then in the next video, we will talk about the LEDs, the electrical aspects of it. Okay. Thank you so much. See you later. Bye.